Hi. Okay. How are you doing?
Very good, very good. Nice,
Okay.
fine. Nice that you can join me.
Yes,
How are
yes.
you doing?
I'm doing good. Thank you. So, how's things from your side?
Yes, here's is good. Yeah, just the quarantine situation is
Yeah.
not so nice. How are things by your side? You're
Actually, in India, the cases are kind of increasing, but Bangalore seems to be doing a little better.
okay.
So, yeah. But we are kind of indoors most of the time, so not
Yeah,
venturing out. So, I think this is a time to stay at home and stay safe.
yeah. And you are doing teaching as well from home?
Not that we generally kind of from DMAT, like we kind of go and do things, on the side. But because it's COVID situation, now we are thinking of going online. Not as started, but we are planning.
Yes, because you're still. Because I see your Instagram posts regularly with nice puzzles. So that's what you're still doing.
Yeah. yeah. So yeah, basically in Insta, and we have a Bangalore math circle. So we kind of keep discussing every day.
Every day. Okay, that's nice.
Yeah.
And who are doing those? Who are participating in these puzzles? Which student from which age are doing that? Or...
Okay, so in our Bangalore math circle, we have people from all ages. From students all the way till adults. So we have. It's a more of a general forum, basically to spread the love for math. So we discuss about everything, puzzles, math topics, everything about math. So it's a mix of different age groups. So not really focused on a particular age group.
But that's interesting. So all ages are participating in joyful math. And it's also being picked up in schools, or it's just by students that are already into math. They're also how is that?
Okay, from school's point of view, I'm working with one particular organization who are actually taking up this exploring dots in particular, right? To government schools. So there's a organization that's actually working with government schools, like around 4,000 plus government schools in our state. So it's in the local language. So I'm working with them to kind of get explain dots, reach them so that they can learn math in more fun and visual way. Because one of the things that they were looking forward to was more of a fun and visual way of learning math, and explain dots kind of fits there beautifully.
Yes, because I understand that the exploding dots idea is for primary school for children to learn see the arithmetics in a different way, but like the later lessons or islands from 6, 7, 8, they get really interesting, and what you're doing is really interesting for higher grades math. So it's really a way of doing mathematics till any ages and also any level, right?
Right. Actually, I kind of recommend Explain Dot to be started in grade 1, because if you look at it, it's like a platform to make kids think visually and mathematically. Because once they get that mathematical thinking, you can actually play with it and keep applying it, the same thing to your higher grade lessons, and it becomes so natural. So you start with grade 1 and you can actually take it all the way till grade 12. Like you start with simple math, right? Like basic addition, basic representing numbers, addition, subtraction, which students do in grade 1 and 2. And then you just take that concept to multiplication, division, and then you take it to algebra, you take it to polynomial division, then you take it to infinite series, then you kind of take it to modular arithmetic, you take it to divisibility rules, you take it to trigonometry, you take it to number theory, right? But what you're doing is the same mathematical thinking, playing with patterns. It's just the same thing you're doing, but actually you're learning a wide range of mathematical topics using the same unified model. So actually, I kind of tell parents and teachers, it's a foundation piece. They have to, once they get it, they don't have to learn everything explorers, but if they get that mathematical thinking, visual thinking, in grade till from grade 1 to grade 5, it's so important, because once they get it, they'll just we don't have to really push them. They'll get the love for the subject, and they can take it forward on their own, because it's just playing. It's just like playing a game. Once if you get a student interested in a game, they're going to play it for the rest of their life, right? So for example, if somebody likes football, it's that initial years. If they like football, okay, in those initial years, they'll continue to be a football fan for the rest of their life. Exactly same concept.
I really love that
but
idea.
if they hate football at their younger year, they will never love football, right? They will never like it.
I love this idea of triggering, of finding out people that the mathematical thinking of children comes out when you play this, when you see the children that are, because in normal situations, children tend to be before of the time pressure, or they don't understand the little part, and then they get disillusionated. I don't know if the word is right, but they feel like, oh, but then I'm not a math person, so I don't like this. But if you play, then it stimulates themselves, and they get really interested, and that's what I also really enjoy about this. But I want to ask, the grade 1, what age is that? Because the levels are here different, maybe. What do you mean by grade 1? What age group is that?
Grade 1 is 6 years. That's when grade 1 starts, 6 years. They can start 6 years is the right age to just start putting dots, because it's just like playing a game, taking a box, putting dots, exploring. It's just a simple game. So there are a couple of games also that we have developed as part of exploring dots. One game is just like the Ludo game, which is famous, right? So very simple and similar to that game, which just gives them an idea, how things work. They don't have to know math to play the game, right? Just like any other game, they don't have to know the math. But once they start loving the game, and when they have to figure out the winning strategy, that's when they start thinking, right? That's what we want them, right? Because everybody wants to win, right? All kids want to win the game. So when they start thinking, then they'll start applying. Oh, okay. Then they kind of naturally understand the number system,
What I also like about that you say everybody likes to win, but with games, you always have losers as well. And I like the idea that children lose because they get used to adopting, not that they get used to losing, but they get the feeling that when they lose, they want to do something about it, so they win next time. So it's not like, you failed, you're a loser, but you get this motivation of, next time I will do better, and that's what you want. And not to feel like, you did wrong, because that is what normally the situation when you have only how you say that exercises and you do them wrong, you get the mark, and then it's over. And in games you can just keep playing and developing, and that's what I like.
Exactly. So in a regular thing, what happens is we generally give students a set of problems. Okay, do this 40 problems as homework. So what happens is what they're doing is they're not thinking, they're just applying rules, right? Okay, to get the LCM, I need to do this step 1, 2, 3, 4. Do this for 40 pairs of numbers. What they're doing is just applying rules. They're not actually thinking beyond, right? It's just like apply the rules, get the answer. Apply the rules, get the answer, right? So they're just more of practicing. It's like memory practicing, right? So that kind of thing. So that doesn't help them develop the mathematical thinking. But when they play, what happens is that they're free to explore the way they want, right? You just throw them the thing and they will explore it. We want kids to get that kind of exploratory mindset, so that, because once you start exploring, who knows, that's how discouraged inventions are made, right? That's the mindset we want in students.
And that they know that they can build up from their own, what they understand, from that they expand. So they just they explore everybody on the same level. I feel that is really important, that you don't start applying rules
Yeah.
just for the sake of it, but you want to really understand what's going on. And yeah, I think children are really honest when they don't understand something. When you give them when you don't give the feeling that they do wrong when they don't give the right answer, but you just give them authenticity, then they really are honest when they don't understand something. And that's what you want. You want children to be really honest and playful and just experiencing. It's really nice. And you see the interaction between children, that they really want to help each other as well. It's really fun. I really like it.
Yeah. And the key thing is like, once they get that mathematical thinking, like, every kid wants to become something, right? Not to become only a mathematician. They want to become engineer, they want to become astronaut, right? They can, right? But what is most important thing is that mathematical thinking. Because once you have that mathematical thinking, whatever field you go into, it is always going to help you in that field, right? So it's very important to get that mathematical thinking. So what we are teaching is not, just like math to make a career in math, but it's basically to get that mathematical thinking, so that whatever field they choose to pursue, they kind of become successful in that field, right? So to become successful in any field, you need that mathematical thinking, right? For example, music, like there are people who say, like musicians who say, oh, I'm not good in math, but actually I feel, music is all about math. So it's like math is like a sense organ, right? I always feel it's like a sense organ. Everybody has math in them. It's just that they don't know about it. Okay, everybody has. So in some ways, I don't think I'm a math person. It really feels odd, right? Everybody has math in them. It's just they have to kind of groom that and kind of use it. It's just like saying, like when you see things, right? Everybody can see things because everybody has eyes. So it's just math is just like a sense organ, like eyes. But what you need is a power of observation, right? How do you develop that observation? Everybody can see, but only few observe. So everybody has math in them. If somebody says, I don't have math in me, I'm not the math kind of person, that's absolutely wrong. It's just that they're not explored it. So that's what we want, students to start developing.
But it's fascinating, because I don't think any child will say from the bottom, I can do that. It's something that it's a kind of mindset that's created, that math is something, and well, I'm not good at this, so I'm not a math person. There's something created. And I think also it's not only the children, probably also adults will help create that kind of image about math. That's why we're in this situation. I think a lot of people don't know what is math. I always say math is everything, because everywhere you see math, but for the general people, math is something just applying rules and try to calculate stuff and get an answer, and that's math. I think.
Yeah, great. Math is all about. Yeah, math is really about thinking. A systematic way of thinking. Right. So. Today what happens in education is math is more in terms of memory. Okay, if you know this formula, then you can do this problem, right? So what happens is, if they don't know the formula, they cannot do the problem. So they think, okay, I'm not good in math, right? Yeah. That's definitely not the way. Math is about how you think, right? You can always solve a problem in, you don't have to solve all the problems, but you just need that mindset, the approach to solve a problem. That is the most important thing. That is math. What is the approach you take?
Yeah, I think, because I always say it's problem solving, but it's not just problem solving. It's just the process of problem solving.
Exactly, the process. That's the most important thing. The process. Yes, you may get an answer or not. That's not the important thing at all. And one more thing is about time. I keep telling students and parents, time is not the factor at all, right? So because a lot of people ask, is it going to help my son do this problem fast? Then I ask, what do you want students to do it fast? Because if you want to do anything fast, we have computers, we have calculators. Okay, we don't need, because machines are going to be faster than humans any day, right? So that is not the competition. The competition is, okay, can machines do the thinking? No, only, right? There's humans who do the thinking. So we need to get that thinking. We don't have to compete in terms of speed. Okay, That's definitely not, that should not come in the equation at all. Be it math or anything, speed should never come in the equation.
Yeah, but the practical side is that we have tests, we have standardized
Exactly.
tests in time. So that's
true.
So,
yeah, that's the practical truth. But yeah,
it shouldn't be the focus. I think the focus, the way I look at it is when you get to a point where you understand what you're doing, then you get better at it, and then you will do the test in time. Don't worry. Just try to focus on the understanding and the learning and the timing comes after. How you say that?
That should come naturally. Yeah, speed should come naturally. Like if you keep doing the same thing repeatedly, the speed automatically comes. But that should not be the focus. The focus should not be, okay, I want to do this because I want to be fast in math. No, that should never be the primary focus.
No, because then you use a calculator, as you say. Why you want to? But I think I always say it's about when you understand something, then you want to automate it so you get better at it. But you don't want to memorize something you don't understand. So that's the difference, I think.
Yeah, exactly. Right? Exactly. Yeah. It's true.
Well, I really like the way the puzzles you invent, and I know you like my dominoes as well. So we kind of had this interaction where we share some nice ideas. I really like.
The domino puzzle, Erik. Like it was an amazing hit. Like when we did the VAT museum in Bangalore, like it was like a 9-day museum. Like we had like more than 20,000 people who kind of visited the stall. It was amazing. Like the domino puzzles, everybody just loved it. Like, few people found it tough, but they didn't want to give up, and that's the important thing, right? They didn't want to give up. They said, okay, let me try. So it was really, and when they got it right, like I remember like one kid, like he spent almost like 30 minutes to do that, but when he did that, the joy he felt, like that was amazing. That's the great part, you felt really like, okay, yes, I did it.
You want that. I really like that, to see that that engagement and the way
it was very engaging. Like it's very engaging, like because it is so beautifully made, right? It is so nice, like visually, it's very appealing. When they used to come to the stall, it was like they used to see a lot of displays, but this used to catch your attention a lot. They used to come here and ask, okay, what is this? And then they used to start. Once I explained, they used to, okay, let's try it. I think it's visually very well made, well designed.
I have now something about fractions as well, and I will send it to you soon so you can also test that. But I want to talk with you a little bit more about exploding dots, because right now I'm writing a piece for the Mathematical Association, and they wanted to know more about the use of exploding dots, like you say, beyond the grade 5. So when it gets really interesting. And I saw some. I will share my screen. I saw some nice things that I. Oh, this is not. I don't know if you. I wanted to share something I saw on your. Can you see my?
Yes, I can see your.
You see the?
Screen? Yeah, I can. Oh, yeah.
Can you see this one?
Yeah. I can see this.
Yeah, this you made, and I didn't saw it on the website of Exploding Dots, but it's really intuitively fine. This is the 1 square root of 2 machine, right?
Yeah, right. So idea here was like like I said, right, like with Exploding Dots, you can play with the rules. You can create your own rules. So now, if you take like a binary machine, for example, right? So 2 dots explode to become 1 dot to the left, right? So that's a binary machine. So now a student can think, okay, 2 dots explodes and goes to the next box. But what happens if 2 dots explode, but instead of going to the next box, it goes next, like the second box, it skips 1 box and goes to the next box? What would happen, right? It's just a game, right? We are inventing the rules. We can invent rules like whatever way we want. So we can try that, right? Like take 2 dots, explode, and instead of going to the next box, it goes to the second box to the left, right? So it basically skips 1 box. So actually now, if you look at it mathematically, so this is basically a root 2 machine, right?
Yes.
Basically your base is root 2, right? So wow, that's amazing, right? So now That's the key concept here, right? So now we can do search, for example. So what we are showing here is, okay, generally how kids learn is, okay, when there's a problem like root 2 plus 3 divided by root 2 minus 1, okay, then they say, okay, we want to get a rational number in the denominator, so then you multiply by root 2 plus 1 on both the sides, like numerator and denominator, and then solve it, right? So that's the rule. So what kids are doing is they're not applying their brain, their mind, but they're just applying a rule, right? So the idea is, okay, now how we can visually solve this problem. So that's what this talks about. So if you look at it, what this is saying is, okay, when you do division by root 2 minus 1, what is actually happening, okay, is basically the pattern is you're basically cloning a pattern. So you have a root 2 plus 3, right? So basically that pattern gets cloned. So if you look at the bottom one, so there's root 2, there's 1 dot, and 3, there are 3 dots, right? So black and red. So whenever you divide by root 2 minus 1, you are actually cloning it, right? So like put 1 dot and 3 dots and 1 dot and 3 dots and just add them up. So now next time when there's something like root 2 plus 5 divided by root 2 minus 1, they know the concept, okay? They don't have to do anything. They just have to clone it, right? So it's just like if you see multiplying by 11 in decimal, for example, right? When you multiply by 11, what you're just cloning it. So when you have 23, you put 23 and 23, right? So right,
that's amazing.
It's just the same concept. It's just the same concept, right?
Wow.
So what we want is to get that kind of thinking for them. Actually, what they're doing here is like multiplying by 11. So what you're doing by when you do root 2 plus 1, you see it, right? So what you're end of the day you're doing is you're multiplying root 2 plus 3 by root 2 plus 1, because denominator what happens is it becomes 2 minus 1, it's always 1. So end of the day, what is in the numerator, you're multiplying by root 2 plus 1. So what is root 2 plus 1 in the machine is basically 1 dot in the second box and in the middle box and 1 dot in the rightmost box. So how do we represent 11 now in decimal? Exactly same way, right? We represent dot dot. So multiplying by 11, how do you multiply any number by 11 in decimal? Exactly same concept here. Exactly same concept here, right? So we get that connection here. So that's what we want students to think, right? So once they think they get comfortable with the subject, they say, okay, now they feel, okay, search is just like anything else. Okay, otherwise what will happen? What happens today is like when they study arithmetic, when they study algebra, when they study search, they think, okay, they're studying something totally different in isolation. So they have that fear, right? So idea is to remove that fear, because once they feel, okay, all these are connected, that fear is gone. So once fear is gone, the traditional way, it's okay, like they can go with the traditional way. But most important thing is to remove that fear and help build the connection, right? That's where I feel, explain dots really helps.
Yeah, but you have to be comfortable with exploding dots for really understanding this, because otherwise you see it like this and you get that fear. But the way the how you say it, the kindness of the images, I don't know another way to express it, but it's like it don't look difficult. So it's you get more engaged, you get more wanting to know what's happening. While if you only see the square roots and the divisions, you probably get less excited. And the excitement and the removal of fear brings you in such a state that you want to know, and then you this is wonderful. And what I think also, like the brain will I don't know exactly, I'm trying to understand the brain more, but I really feel that visualization is really important for your deep understanding, and this helps so much to understand the way the patterns, to understand the patterns. And I really love this idea. I already found it interesting, but now you explained this to me. Wow, it's amazing. And this kind of things you just find out by just trying, or just how do you come up with it?
I just play I just play whenever I look at, I just keep playing because for me explain out is like it's a game, it's like a toy, like so I just keep playing. Okay, I see, okay, what happens if this happens, this comes here, okay, what happens if instead of becoming a dot, if it becomes anti-dot, right? So you can create your own rules. So I just keep playing around with different rules, and my kids also, like, they are like, my daughter is in like 10th grade and my son is in 7th. So
yeah, they
when
get the age
they
that they
kind
also
of,
want
yeah,
to
they're the age where they come and ask me, okay, how can we do this? And they are kind of excited about explain dots. So they come and ask me, how can we do this in explain dots? Because I feel like, like it's a very intuitive way of learning things. So it also puts me into thinking. So I kind of think and say, okay, yeah, let's do this. And trigonometry was exactly one such thing. Now, when my daughter was started learning trigonometry, okay, we thought, okay, yeah, this, how can we really connect what she has learned, right, in her lower grades, right? She has studied arithmetic, algebra. So when you look at it, finally, trigonometry is just similar to any arithmetic and algebra problem. But the only rule is that, the only thing is that there's an extra rule, right? The extra rule is that sin squared theta plus cos squared theta is equal to 1. So when you put it visually, what it means is basically, if you kind of represent the whole trigonometry, in an explained dots machine, like you have x-axis as sine function, the y-axis as cos. So now what happens to the other side of the sine? So that becomes cosec, right? What happens to the other side of cos? It becomes secant, okay? And the diagonal becomes tan, right? This is tan and this is cot. So you get everything put in a 2D board, right? So and then what you need to do is you take one dot and it exports into two dots. So basically you're saying one is nothing but sin squared plus cos squared theta, right? So you just apply that rule and you can solve trigonometry problem just like you solve your algebra problem. Exactly same, right?
I remember that I saw those visualizations. You really made I don't know if you can. You have one there you can share, or you?
Okay. Let me see. I think I can share.
I understand it. I see it in my head now but I saw already a picture of that one.
Let me see. Let me check. Can you see my share?
Yes, this one. Yeah. That's the one that you showed me that time.
Yeah. So if you look at this two-dimensional explained dots machine, right? So the green axis basically represents cosine, the yellow one is the sine. So the blue becomes like the secant, right? So 1 by cos, and similarly the orange one becomes cosecant. And if you look at the diagonal one, the red is the tan, so the purple becomes the cot.
Yes.
Okay. So now we can actually solve problem, like if you want to find out, okay, what is secant theta plus tan theta 1 minus sine theta. So what we are actually doing is we are putting secant theta plus tan theta. If you look at the one below, right, there's a dot here. So this is nothing but tan theta, right? This dot represents tan theta, the one on the red. Yes. Okay. Then the one on the blue represents secant theta. So basically these two dots represent secant theta plus tan theta, right? So now we need to multiply that by 1 minus sine theta, right? So okay. So multiplying by 1 is just putting it there, and minus sine theta is like anti-dot, and sine theta is like one dot yellow thing. So basically we need to shift this to the left by 1 and it becomes anti-dot. So multiplying this is basically putting two white dots here, one another and one here, right? One here. So now these two dots and line dots kind of explode, and because they cancel out. So what you are left with is anti-dot here and a dot here, and now in an algebra problem, okay, it just stops here, right? So basically your sum is basically this anti-dot and a dot. But in trigonometry, we just take that one, we put that one extra rule. This dot here, okay, this dot on the blue one can explode into one dot here. Basically what you're saying is one is nothing but sin squared theta plus squared theta. So now this dot goes one here and one here. So these two cancel, and so we get one dot on the green one, and so it's nothing but cos theta, right? So
yeah, that one the anti-dot and the dot and the green part that becomes one in the green. Why is that?
Okay, so the key. Okay, so the rules here are exactly the same as in any explained dots machine, but in trigonometry we apply one special rule. If you look at it, maybe I can draw. I can just put some. Okay. So if you look at this in trigonometry, right? One dot here. Okay, it represents 1, right? Now, what does this represent? This is sine square theta, right?
Yes.
Because this is sine theta and this is sine square theta. Similarly, what does this represent? Cos square theta, right? Yeah. So basically, what in trigonometry, what we basically do is, whenever there is sine square theta and cos square theta, we replace that with 1, right? Basically, sine square theta plus cos square theta is 1. So whenever we have one dot here, okay, if we have one dot here, if you have one dot on here, okay, so that becomes one dot here, right? So, and the reverse is same thing. If you have one dot here, it becomes one dot here, and it becomes one dot here. Okay. It becomes one dot here and one dot here. So basically, in other words, a dot on the yellow and a dot on the green together explodes, and they become one dot on this white, or one dot on the white kind of unexplodes and becomes one dot on the yellow and one dot on the green, the reverse, right? So that is what we are applying here. So coming back here, so we have one blue dot here, right? So this blue dot becomes one dot here,
there. Now
and one, one dot there, one dot there, right? So, and the blue dot cancels. Now that's what is there in the next right figure. So here these two go cancel off, these two cancel off, and what is left is only this one. What is left is only
that's why the one that down also disappears. Yes. Okay.
Yeah, it's like dot and a dot. So we actually, what we are doing is we are exactly playing the same way as we did with arithmetic and algebra. Okay. Only extra thing is that we are putting one extra rule, that sine square theta plus cos square theta is equal to 1. That's the only thing we are putting. Okay. Using that, we can solve any trigonometry identity. Okay. So now when I taught this to my daughter, like, the very intent is that, it drives away that fear that, okay, this is something, a different subject. They get a feeling, oh, this is exactly the same thing I've been doing for years. I'm just putting some additional rule. Otherwise, it's just the same thing. Now that fear is gone. Okay, once that fear is gone, they feel very comfortable. Oh, trigonometry, oh, that's easy, right? They get that feeling, okay, it's easy. Okay, I think that's the hurdle we have to make children pass. And so once they pass that hurdle, the rest is easy. They can, because in the practically, if you look at it in the examination, they may not be able to do this way, right? Because this is not the way, right? In the examination, they are supposed to do. But what is important is once they do it this way, they get comfortable with the subject, and they can still do the traditional way, but they can always quickly fall back on this. If they don't understand something, they can quickly verify.
Well, you explained this is amazing, because like the focus, or the most important thing is not only the joy but also the removal of fear. And I hear James say that a lot, but now I understand more about it, because it's not about you have to do those problems in this way, but this way lets you get the experience that it's okay, that it's not rocket science. It's just the same. It's just math. It's just some rules that you can apply, and you already know those rules, but just it's in a different way. And then once the fear is removed, and you see that it's not so well, that it's difficult maybe, but it's not. It's not something you are not able to manage when you get when you get into it. Then that's the thing. I think that
exactly. Idea is to connect the dots, because students today kind of learn a lot of things from grade 1 onwards. But what happens is once they come into some grade, they kind of they're not able to correlate, okay, what they learned in the previous grades, right? And so what Experiment Dots helps is basically build that link, like connect the dots, because once you connect the dots,
your brains,
yes, exactly.
What I think is that some children, that when they don't understand something, they learn it, but they put it somewhere. And that
it's in a silo.
Information is just separated from how they normally would solve things. So it's information that maybe is powerful, but only when you're there. And when you're not there, then you don't use it. And that's why children sometimes think they are good at arithmetic, while they say, well, I can do arithmetic, but I'm not good at math. And that's that separation of calculus, I think. Is not separated from math. If you teach it in another way, and that's what Exploding does helps you to realize.
One of the examples I kind of give whenever I give talks on Exploding Dots is I give an example of this connect the dot book, right? So every kid would have played that, right? So basically, where there'll be a series of set of dots, and you need to join them. And
Yes.
once you join, you will get a house. You will get a dolphin, right?
Yeah.
Now, math or any subject is very similar to that. Okay, the dots represent a different concept they learn, but there's only one difference. In Connect the Dots book, they give you the numbers. Each dot is numbered 1, 2, 3, 4. So they know, okay, from 1 they have to go to 2, right? So they connect everything and they make a picture, right? So basically, what it's saying is, only when you connect everything, you get a meaning out of it, right? You get a meaning out of the dots.
Yeah.
Now let's apply it to math, or particularly math. Okay, so now whatever they're learning in school, right? Algebra, arithmetic, they're like dots. Okay, they're learning it, but to make a meaning out of that, right, we need to connect them. Unless we connect them, there's no meaning. It just remains as dots, right? Just like a picture. Now to connect them, the only difference is that in that Connect the Dots book, it is numbered. Here it is not numbered. We need to number them, right? That's what the kids need to do, because it's very important. Because nobody is going to tell them, okay, this is the numbering. Okay, so they need to connect it, and how they connect it, that's their mathematical thinking, right? There's no strict rules. They can connect whatever they want. That's how invention discourses are made. But it's very important to connect. If they don't connect, it remains as dots, and there's no meaning.
Wow, it's like saying that you have a lot of dots and you can make your own image, but if you don't connect, you will never get an image. Oh, that's amazing.
Exactly.
Yeah.
Right.
Oh.
Right. So this is an example I kind of give to help, because it's very important to connect them. So I feel Explain Dots helps the connect. It helps connect a lot of things, like arithmetic, algebra, trigonometry. So that students get that feel, okay, it's all related, right? So they feel more comfortable, and they can actually visualize better what's actually.
I do a lot of fold. You see that I also do with folding, and then I'm trying to connect it with wiskunde as the geometry. And I think that is really powerful to just connect, different things to really see that math. I always say math is everywhere, but that exploding dots is for the algebra so powerful, and I really want people to see that. So I was thinking, I have to talk with you because I see you do so many beautiful things, and how I can never explain it yet the way you do. So I'm so grateful that you take this time for talk with me about this. And you're okay that I use this video for a show, right? Yeah, we already talked about it. No, it's okay. I'm really happy to have been able to do this talk with you, and I will put subtitles on it so people can understand it, and whenever it gets published, I will send you. And
okay.
We'll stay in touch. Next week I will start really producing my game with the fractions, and then I will send it to you, and then we'll.
I'm looking forward to it.
Yeah, well, really, thank you so much for your time. It's an honor and a privilege, and I really love it.
It was a great pleasure. Nice talking with you. Yeah.
See you.
See you, Erik. Bye-bye.
Bye-bye.